Good afternoon, everybody. Welcome to this, third, let's say, contact moment that we have together. I call it my second lecture, but it's because I start numbering from zero. That's the crazy scientist in me that does that. So today I will be talking to you about the second aspect of my lecture series that I wanted to present to you, and that's the state of the art in the isotope separation online technique. The short for this is ISOL, so you're going to see a lot of ISOL coming all over. And of course, my favorite facility, the one in which I did my PhD, with whom I do still most of my research, that's Isolde, the ISOL device at CERN. So you'll see Isolde, of course, very often taken as an example of the facilities I want to describe to you. But first, let's have a quick recap about what we discussed last time. And last time it was about just the pure production of the radioisotopes, so not the production of a beam of those isotopes. And we said there that the two key ingredients were the luminosity on the one side and the cross-section on the other side, and then that your production rate was simply the multiplication of those two together. So the cross-section determines what beam you work with, on which target you shoot it, and at which energy you shoot that beam. And that determines basically your cross-section, so how much you can produce. Next to that, you have the luminosity, which itself is just the product of how much beam and how much target material you have that can encounter that beam. So ideally, you want more primary beam and you want more target. That should be relatively easy, and that way you increase your production. But there are always, caveats about that. What about purity? It's not enough to say you want more, but you want also cleaner. Because if you imagine working with a medical product, your product has to be clean. It has to work completely and effectively, and you have to make sure you don't induce unwanted damage to your patient. If you want to study also a very rare process, you want to ensure that all you're going to see is that process. You don't want to carry too much background with it. That's going to drown out the science that you want to do. So purity is really a key factor in radioactive ion beams, which is why we actually have to look beyond just those raw, let's give it more power. And actually, many facilities nowadays that just go for the power end up struggling all along the way to make it happen because it comes with added challenges. And we'll come to that towards the end of this lecture. But first, a quick recap of what the ISOL method is. This is a video I presented to you already that describes how this works at Isolde. And here you have a picture of the front end, where the primary beam of protons in red here impinges on a thick target about 20 centimeters long, and that induces a whole lot of different nuclear reactions. All those recoils are captured in the target material, and with high temperature, about 2000 degrees Celsius, they extract it from the ion source, from the target, bring it to an ion source, and create a positive ion beam from it. By keeping this entire system at 30 to 60 kilovolts of potential, they manage to extract it from that front end as a beam. And then you can see how that monoenergetic beam is subsequently analyzed through the homogeneous magnetic field of a dipole magnet, which then separates the beam according to the mass over charge. The typical ion source will give you a 1+ charge, so those are called mass separator machines. And that delivers then to the focal plane a beam of, hopefully, the isotope you're interested in that can then be further transported to your favorite experiment, or simply collected on a foil. But okay, sounds relatively easy when it's just highlighted like this. So why do we have to look, what do we have to dig into to better understand this? And that's basically the outline of my lecture. You start with the target. What are the requirements of the target to make this work? We'll go through basic concepts and maybe some new innovations that are ongoing as well. Then you come into the ion source. An ion source is not just a simple device. Actually, you have many ion sources depending on what you want to do, and those depend on whether you want ultra purity, high intensity, and different aspects of those. So I have chosen 3 of the most common ISOL ion sources for this discussion that I'll introduce to you. Then you can manipulate this beam. It's not just that you produce the beam, but then you can look at how the beam is structured and what you can do with it and whether you can play along with those parameters. And finally, I'll come to post-acceleration. It is an essential part of working with radioactive ion beams that basically open up a completely new array of experiments. It is my understanding that post-acceleration will not be foreseen at Isola Mira, so that is indeed a bit outside the scope of what is done at the SCK, but from my KU Leuven perspective, it is a big part of our research there, and I think that it's quite interesting to see how it works, but also maybe to understand why is it so much extra weight that should not be considered as a first stage when you build a new ISIL facility. Okay, so let's start with the ISIL targets, beyond just maximizing luminosity. Because if you think about it, if you want the most material you can possibly have, you're going to make that material as dense as possible, which of course is not what we're going to be wanting, and you'll see that by the end of this section. Let's actually look at the isotope release. That's maybe the step after the target. Remember in that video, it magically comes out of the target. Well, there is science behind that magic. So let's see how it goes in more details. You've got the protons coming onto the target, you've got the ion source. We apply very high current on somewhat small potentials on those two devices, on the long tube, the target, and the tiny tube, the transfer line and the ion source behind it. But you see there, you can apply up to 1,000 amps on those devices. That's a lot. And that's to have resistive heating through the material so that you can reach those high temperature, 2,000, maybe up to 2,500 Celsius. Inside the tube, you have your target material. Now, if you think the example that's given here, it's a powder compact made of grains that are loosely connected with one another with big pores in between. The idea is that the protons induce your reaction inside that grain, and then you have the processes we've discussed last time that determine the yield of what is produced within that grain. So that includes your beam intensity, your number of target atom, that's the IN at the front, the luminosity, and then you've got the cross-section, which you have to integrate over the energy, considering the energy loss through the material. And then comes at the end an efficiency, how much you really see at the end of all those yields you've created. And that includes the diffusion of that recoil through the grain of the material in which it was produced, coming to the surface of that grain. And from there, it has to desorb and effuse through the pores of your target material, come to the surface of that target, and effuse through the target's container and the ion source and transfer line. Finally, you have to create an ion. This is also not something that is guaranteed. This is something that comes with its own efficiency on top of it. And then you have to separate those isotopes and transport them to their final experiment. And that means at each stage, you may have quite a lot of losses. So you see how the efficiency of every step is going to be crucial in order to have a high intensity radioactive ion beam. And when you look at all of those, one of the processes that's critical is actually the diffusion in the target material. That's one that's holding everything back most of the time. It is not that your efficiency is completely, well, sometimes it is going to be zero if the chemistry holds everything in, but sometimes it is just going to be adding a delay. But when you convolute that with a half-life, then it's going to be a big loss in decay losses. So how do you enhance diffusion? Then you look at the top at the Arrhenius equation, and what it basically says is that it goes exponentially with the ratio of the energy that's required for the diffusion to the temperature you apply. And that means you want to run at as high a temperature as possible. We'll see very soon why it is not always possible. But then what you see as well in how all of this turns out when you turn it into a full-fledged efficiency, it scales like 1 over the grain size. And if you think about it, it's somewhat logical. The smaller the grain, the faster it's going to be on the surface of that grain, the lesser it has to diffuse. So then you can get things out much faster if you work with a very small grain. So if you can control the microstructure, you can enhance the release properties. That's great. So how small can we go in grain size? This is a bit the challenge of many of those target materials. And then we start with the easiest target you can have, just a piece of metal. It is the simplest form, and simply because you can reach high densities with metals, that's not a problem. The reaction channels are very simple. You have one beam coming onto one target, so you know exactly what you're going to create. And then it is also easy to handle. I mean, of course, some metals might be more complicated than other. A thorium foil will require a lot more attention with respect to radio protection than a titanium foil, but nonetheless, metals are stuff that we can handle, we can manufacture, we can make them into thin foils if we want to, and so on. So this is something that's quite easy to deal with. But there are challenges. Then I come back to you. Now, I'm asking you the question, how do you release the recoils from the target material? I've said it 2 or 3 times today. What's the key in getting things to come out? Temperature. So, you want to run that metal at high temperature. What happens to metal at high temperature? It melts. So, what is important is you have to maintain the integrity of your material. And that's often a limit in working with metallic foils. So, what sort of metal can you use? Refractory metals. They tend to have a very high melting point, so you can actually operate them at very high temperature, so that's going to be great to work with. And one that's typically used are rolled tantalum foils. And I really mean like this. I showed that picture as well in the start in my inaugural lecture. This is how the tantalum targets at Isolde are made. You can see also on the top right what can be produced at Isolde with 1.4 GeV protons impinging on those tantalum rolls. And you can see you produce already a lot of isotopes. Naturally, they always have to be lighter than your target material. And the rolls you see there are actually made of 20 micrometer thick foils. And you roll them so that you can keep them very thin and allow for the fast diffusion across that thickness, but also maintain a sufficiently high density that your luminosity is not affected by the fact that you actually work with thin foils. So that's sort of how you have this trade-off between having something very thin, but still having a decent enough density. Now, if you imagine you would be working with a cylindrical block of tantalum, then your diffusion would be so poor, so bad, nothing would get out. You'd produce a lot of radioactivity, and it would all be trapped in that big stick waste. So that's how they make the tantalum targets. Yeah? No, it's natural. Yeah. I just put 180 because that's what came to mind when I was typing, but no, it's natural tantalum. There are some cases in which we work with enriched material, and I'll come to that in a minute. So if you cannot maintain the integrity of your metal, then simply deal with it and start from the principle that your metal is just going to be a big lump of something molten. And that's what we do at Isolde with the lead target. Once again, to answer your question right away, I put 208 here, but we use natural lead. So lead is also a heavy element, and you can see on the top right everything that you can produce from our lead target. And you see it goes a bit further because it goes, well, up to lead 208. Since it's a soft metal, it would not sustain the hot temperature, so instead of taking the risk, you go and immediately say, let's melt this. And this is the sort of design that you can see for this target unit. where actually you have to make a bit of an added design. So you can see here how you're not going straight from the target to the ion source, but you've got this contraption to go about first, with here, also represented there, a chimney that will allow you to condensate the lead that might be coming off and let it flow back into your target to avoid that lead leaving your target unit, going through your ion source and coating everything on the way. We've actually had sometimes difficulties with this target that we started to build up lead on top of our extraction electrode. The buildup was not uniform, and then it started created little points off of which sparks would start to come off on our 60 kilovolt high voltage. So it is non-trivial to work with those. And of course, if you start thinking about such a target, there was a high intensity version of that was researched for a very long time, and I believe quite a few of you are familiar with the LIBE project, where it was a molten lead bismuth target that was to be investigated with that. And in order to avoid some of the deterioration of the material, instead of just working with a container, it was supposed to be a loop, and that would allow also faster diffusion from the material by having a smaller sample from which the radioisotope had to diffuse. But this has been a very long endeavor and has never quite achieved what it was aimed to do. So nonetheless, to come sort to a conclusion on those metallic targets, you have here the summary of what Isolde uses quite frequently. And on the metal foil, we will use titanium or tantalum, depending on the isotopes you would like to produce. Or for molten metals, we can use molten tin, molten lanthanum, and molten lead. Okay, those are okay targets, but how can we get thinner materials that will actually release faster than that? Because 20 micrometer is still pretty thick, and from those molten targets, well, there are speculation about a splashing effect that could create droplets from which things are released faster and so on, but it's never been quite conclusive how to go to the shortest lived isotopes. So let's go to another type of target, and that's the ceramics. Ceramics with controlled porosity. So everybody's favorite then is uranium carbide. And you can see here what you can produce with uranium-238. So you see that you go, again, much, much further than what you could do with the lead or with the tantalum. And this time, we're actually talking about uranium-238, not natural uranium. It's the most neutron-rich heavy isotope that can be found in large quantity on Earth. Actually, its N over Z is 1.59. I looked up just for the fun of it what's thorium-232, and it's 157. So it is indeed better than the thorium in that respect. It's also fissile. So you can use it to produce fission products in this region, which is quite a nice way to go to neutron-rich material. And it keeps the same N over Z ratio. So if you apply that with a Z equal 50, you actually end up with somewhere between tin 129 and tin 130. Now, if you dig back into your memory of what are those magic numbers again? 50 plus 82, 132 tin is a magic number. It's actually the one that's highlighted here where those two black lines on the nuclear chart cross. And so that's the point at which a lot of research is going to be extremely interesting, and that's the type of thing that has been quite prominent at Isolde, for example. And we actually work with enriched uranium-238, which, funnily enough, is the depleted uranium, because you actually typically want to enrich in 235, not in 238. So we basically take the waste from 235 enrichment, which you would think, oh, wow, people are going to be happy to give you that. Well, no. It is still considered an enriched material and therefore a controlled substance. So it is harder to get than natural uranium. And we always have to be quite attentive in how we procure our uranium. That's also always coming into with some sort of impurities that can be quite impactful later on how you try to work with your target. And you can see here an image with secondary electron microscopy that was performed on such uranium carbide target, where you have a bit an idea of the microstructure that it can have. There are also some lumps that can be seen in there. I believe that here is a lump, and that's actually coming from something I'll describe now. And it is how difficult it is to actually control your production of uranium carbide. Because uranium is not quite very, very stable in its carbide form. If you always think about how is uranium found typically in minerals or when it's being handled, or handled in the sense of marketed, it's always uranium oxide. And if you create a uranium carbide, it's actually very easy to oxidize. Lanthanum, which is the lanthanide equivalent people work with to practice their carburation process, if you take a little pellet of lanthanum carbide and drop it on the table, the energy that's being released from that action is sufficient for it to spontaneously catch on fire. So try to tell then to your radio protection officer, I'm going to do that, and the same will happen with uranium. They will not be very happy. So it's something that is quite complicated to handle and requires a lot of overhead and attention. So you start from a supply of uranium oxide. You perform yourself the carburation. That's how it's done at Triumph and at Isolde, for example. I believe that SPES is also developing its own recipe for this. And then your target material must be kept under argon atmosphere to prevent oxidation. So it's something that comes with its concerns and challenges. The second thing is the exact form of uranium carbide is not quite well known. I mean, the phase diagram is well known. You have an extended version of that phase diagram here as a function of the carbon content and of the temperature. But what you can see is it's got a lot of phases and it's got a lot of places where it can change phase. So typically it will depend on how much carbon you've put into the system and at which temperature you operate. Well, first, at which temperature you perform the carburation, but then during operation, depending on at which temperature you operate. So we typically name those targets UCX, where X is somewhere between 1 and 2. And it's typically a mixture of UC1, UC2, and graphite. Because there are some lumps of graphite that can also form in the process. So this is something that, of course, can have quite some impact later on in terms of the sintering processes and the pores closure during operation. So what are the limits then of such a uranium carbide target? First, some other elements can form very stable carbides. I was talking just before about lanthanum carbide. It is one example, but actually all the lanthanides will form rather stable carbides to the same extent as uranium carbide. But it means that if your target is maintaining its integrity as uranium carbide, all the rare earth elements will stay in that same material as very stable carbides. So there is no way you can actually efficiently extract those rare earth elements. And if you look at actually how all the rare earth investigation and studies have been performed, they're always done from metallic tantalum targets because of how hard it is to get them out of a carbide material. Then the other thing is oxygen. Any trace of oxygen you may have will immediately give you a fantastic CO beam. So they actually have very good CO plus beams at Isolde. Unfortunately, it's typically carbon-12 and oxygen-16 and not much else. So even there, it's difficult to get the radioactive ones to come out. But it also means you can have a lot of chemistry happening in those targets that can become quite problematic. There have also been issues of very intense chromium beams coming out of those targets. And it's actually due to chromium that is left behind in the uranium from the uranium stash that they were able at Isolde to acquire. So even there, very limited trace amounts of some material can translate into very intense stable beams that could potentially compromise your experiment. So this is something you have to be very attentive about. The second point is what's happening with your grain size. It will depend on your starting material. So typically, people work with micrometer scale grains. 1, maybe up to 10 micrometers to try to keep it small. If you remember, tantalum foil, 20 micrometers, we tried to go smaller than that. So that's why the 1 to 10 range is already a very good progress. But there, you are facing with the challenge of sintering of that target, either during the preparation phase, when you put those grains together and try to compact them into pellets, or when you are operating at high temperature. And there, you face 2 solutions to go about that. You can start with nanometric material. 1 micrometer is already too big. Let's go to 100 nanometers, 50 nanometers, 20 nanometers. Anyone anything better? If you just keep going smaller, it should go better, right? It scales like 1 over the grain size. And if you don't want sintering, work at low temperature. That's easy. Well, yes, but what about the diffusion? So you see here, it's the opposite problem. With the metal, you would want to push the temperature higher. You're limited there because it's going to melt. If you go to ceramics, you say, oh, let's now push it to higher temperature. But there, what you get is densification, pore closure. You also kill your diffusion. It's not the integrity of your material, but it's the release that you are going to kill in that process. So sintering, what are the 2 issues that you may face with target sintering? That's a rather simple model, a slide that I stole from one of my PhD who probably stole it from somewhere on the internet. But the point of here is that you have 2 things that can happen. First, your grains here, which loosely touch with one another, may start to coarsen. Basically, they are merging together and forming bigger grains. Bigger grains means more material to diffuse through. It's like you went to nanoscale material, but you actually immediately go back to microscale material. So where's the gain? The second point is those little spaces between the grains, the famous pores through which you have to effuse. And here you have what is called densification. Instead of having grains that just touch at some boundaries, all the boundaries start to fuse together. They're still independent grains, but they close up the pores. And there you see there is no place for the material to effuse anymore. And of course, you can get both of them together, and that's the worst you can possibly have for an isol material. This is what you're hoping for in terms of typical ceramics. You want to go to high densification of your ceramics. We want the complete opposite. You want a very poor ceramic, one that's going to stay poor as well. So it seems a bit contradictory, but it's just, well, another application of the same concept. But what is quite interesting to see, and I did not know that before I started having a student work on it, those 2 processes, they actually are enhanced for nanomaterials. If you have a very, very good nanomaterial where all your grains are perfectly the same size, it is going to be the best way for you to go to full densification. So actually, when people say, go to a nanomaterial, the consequence is that you accelerate the sintering. And they've typically been observed to perform poorer than the micrometer scale targets. Or maybe they start well and they degrade very fast, much faster. So you need to find a way to maintain this structure and this matrix in order to get your system to maintain its release properties. And that's a bit of a challenge. Every time you try to find a solution, physics plays against you and tries to punch you back. And so you have to find ways around it. And that's where really going into innovative target material design becomes quite challenging. And it's built upon a lot of trial and error. So how do you design your best uranium carbide target? You want to enhance the release. So you want nanograins to keep the diffusion very fast. You want to run at high temperature to keep the diffusion going quick. And you actually potentially want to inject CF4 or O2 to promote the release of maybe molecules that are more volatile and will effuse faster. But then you have your operation limits around it, which means don't work with nanomaterial because you don't want sintering. Well, that's a bit contradictory. Oops. Run at low temperature to minimize sintering. So that's contradicting the high temperature to keep diffusion going. And run in as pure a vacuum as you can to prevent the degradation of your uranium carbide target. You don't want it to suddenly start oxidizing on you. So you can see that whatever you say is going to improve your system, it's going to destroy it as well. So it's finding this very difficult balance or ways to reconcile those different aspects. That's the whole challenge of targetry for an ISIL facility. So how can we reconcile all of this? Well, there has been some ideas. So one of them is, how can you stabilize this uranium carbide material? And there are two ways that have been explored around Isolde. The first one is the middle picture here that has the A and B inset. It's actually to use multi-walled carbon nanotubes as a form of matrix in which you embed your nanomaterial. And then this nanotube structure is preventing the sintering. It's ensuring that your grains do not get the chance to touch with one another and to sinter with one another. The immediate consequence of that is your X in UCX is no longer between 1 and 2. It goes much higher, so your density goes dramatically down. But your release goes dramatically up. So it is actually something that could be an added value. Could be? No. Is. They actually measured that. That's the work of Alexander Gottberg, reference here and shown up there, where you can see the comparison between here at the bottom, the high density uranium carbide target that they could work with a density, okay, it's not written here, it's in the paper, it was about 30 gram per centimeter cube, 13, whereas their standard, which is the blue curve, the conventional UCX, is the one that has about 3, so a factor 4 down, and then you have the one with the carbon nanotube, which was 1 point something. So it was in itself a lot less uranium material. However, you can see in the red curve how much higher this nano UCX target was performing, but also how much longer. So here we're talking about a time structure from a single packet of protons impacting on the target, how long you could keep seeing some sodium-25 beam, and you can see the amount that you saw with that one, which basically would be the integral under the curve, is substantially higher if you work with that multi-wall carbon nanotube structured nano UCX target. And the other thing you can see underneath is, as part of that study, so now it was done with sodium-30, a lot more exotic species with a much shorter half-life. And you can see here how with the conventional target, at the start you could get more, but very quickly in terms of total operation time, so the proton irradiation time underneath, it is this time how long they've been working with this target. So we're not talking about a single proton and looking at everything that comes from it. We're now looking at how people operate in the long term and the reliability of that target. And you can see how your production is going down exponentially. And this is actually because of the sintering. Your material is just closing down and short-lived species do not manage to come out in time anymore. However, working with the nano UCX in this nanotube matrix, they managed to maintain over quite a substantial amount of time, I mean, it's beyond 10 days here, to manage to keep the yield steady on those very short-lived isotopes. So that's definitely something that is extremely desirable if you want to have a long-term, reliable operation. And one question you could immediately ask is, why don't you run all the experiments with that? Well, manufacturing those takes dedicated facilities. If you have a nanomaterial, you have a huge surface area of contact. It means if it was likely to potentially ignite before, now it's definitely burned down to hell as soon as it's going to encounter any oxygen. And they started to work on, when they designed this nanomaterial, when they produced these amazing results, they did a second batch of production. And then something happened. There was a bit of a hiccup in the production chain, and the uranium carbide fell to the floor. And it spontaneously ignited. because the nanomaterial had such a high surface area, as soon as any oxygen came nearby, it would consume the carbon that was in there. So they realized at that point how dangerous those nanomaterials were, and they said, okay, fine, you can work with that if you build a dedicated laboratory. Publication 2016. We are now in 2021, and they hope that their nanolab will be ready to open next year. So we're talking 5, 6, 7 years to make that happen. It is non-trivial, but it's coming, and we have good hope. Another aspect which I wanted to highlight here is a different concept that was designed, and it's nanofibers. So it's a group in Lisbon who have been researching how to actually spin fibers that are based on uranium. And in their investigation, which are reported in this work here by Sanjay Chaudhuri from Lisbon, they actually managed to demonstrate the high reliability of those fibers and their long-term sustainability. So this is another alternative to observe and produce those innovative targets. Okay, so let's see what are typically the ceramic targets at Isolde. Uranium carbide, as I said, it is everybody's favorite. You can produce almost the entire nuclear chart with it, and it can yield very neutron-rich nuclei. Another one that's quite popular is lanthanum carbide, because it is very good to produce neutron-deficient material with spallation that are not too far from it, and that goes especially to the region of tin 100. Even if we have not been at Isolde able to produce tin 100 yet, we've studied, for example, indium 99, silver 97, 96. We've been able to investigate down to tin 103, tin 102. So there are a lot of investigation closing in on tin 100 that have been performed. And I mentioned that because it was one of the cases that I discussed last time on the fragment separators. And then silicon carbide, which is very suited for the production of light beams. But you may also use oxides. There's nothing that prevents that from being a suitable target. If you can make a ceramic from it, that will sustain the high temperature and the operation conditions. So actually, thorium oxide is one that can be used as well as sort of a replacement for uranium carbide, especially if you want to produce something that is already in an oxide form. Well, you have your plenty resource of oxygen in there. And calcium oxide, I mentioned here, although he's not in the room today, many of you will know João Pedro, and actually his PhD thesis was the design of a nanoscaled calcium oxide target with which they were able to produce the most intense and sustained beams of radioactive argon ions from the nanograins. And to give you a bit of an impression of, okay, from those many targets and many more, because I've not listed them all, what is a typical breakdown? And I have for you the last completed year that Isolde did. That was back in 2018, before the Sun Long Shutdown 2. And you can see here how it's broken down with about 2/3 of the beam times operating on uranium carbide. Now you can see why the demand on this nanolab is so important. Next to that, you can see a few of the molten targets. You have lead, you have tin here that are for specific experiment, tantalum and titanium for the metal target, and then also that one is a metal target, the iridium, titanium, tantalum, tungsten. That was for a specific test. There was also a thorium carbide, zirconium oxide, and hafnium oxide. So you can see like there is, depending on what you want to do, or if you want to do special tests, that there can be a lot of different options to work with. Do you have questions on targets before we go to ion sources? Okay, let me jump then straight into the ion sources. Here, again from Isolde, you have an overview of the elements that they have been able to extract and which ion source was used for the different of them. You can see first that there's this big gap in the middle here, this gray area. Those are the refractory elements. They just do not come out of your target material. Chemically speaking, you just cannot get them to come out. So that's the limit of the ISOL facility. If you want to produce those, either you go to a fragmentation facility or you go to a thin target ion gas catcher facility where you are not limited by your target chemistry. But if you talk, like, let's go to maximum production, well, you're quite limited on those. The key into ionizing something is the ionization energy. You want to bring an electron beyond the ionization threshold. So there you can see that there are definitely some systematic trends in those ionization energies, and that they will have a big impact on what ionization mechanism you have to use for your ion source. So let me start with the the easiest, the simplest of the ion sources. Someone in this audience will recognize those pictures. And I start with surface ionization. The idea there is that upon contact with a hot surface, a loosely bound electron will be kept by the material and your species will come out as an ion. So that will depend also on the match between the work function of your material and the ionization potential or ionization energy of the element that you're trying to ionize. So it must be a material that holds its integrity at high temperature. You need to go to this 2000 degrees Celsius to do that. So you can also not use whatever you want. You have to use something that's quite good. Typically a refractory metal. And the three that are very often used are tungsten, tantalum, and rhenium. And here you can see their work function listed. And so what does that mean in practice? It means you have sort of a cutoff in what you can effectively ionize, which corresponds to those energies plus that temperature together gives you a bit of a threshold around there. And you see immediately what is surface ionized. It's going to be all the alkali elements, maybe the alkali earth, and typically the rare earth elements are also going to be surface ionized. The others is going to be a bit more complicated, although you have some special one that dip in, like I believe this to be gallium, that's going to be to do indium, and that one I forgot what it is. But you can see that there are a few in there that will also creep in. You can also turn that around. If you can steal an electron, maybe you can give one away as well. Then the idea is the opposite. You have to look at something that will be very likely to grab an electron on contact and comes out as a negative ion. Then you want to use here a material that will be likely to give away its electron as well. So then you don't look anymore at the ionization energy, but now at the electron affinity, the likelihood of grabbing that extra electron. And you can see the trend is somewhat different, but those that are clearly at the top are those. And in practice, it can only apply to halogens. So those are typically the negative beam we produce. And Isolde, I don't believe we've produced negative fluorine, but we've produced negative chlorine, negative bromine, iodine, and negative acetine for different experiments. There are other ways by which you can produce negative beam, but typically it involves starting with a positive beam and then in flight grabbing 2 electrons by passing it through a vapor that will be likely to give away its electrons. So I do not discuss this in the beam manipulation section, although that could have been a subject. I had to make choices at some point. I see as well that we're running already over time with respect to what I had planned. So let's hope that I can give you most of what I wanted to say for the rest. The next type of ion source that we work with is the electron impact ion source. So in this one, you actually use a stream of electrons to impact upon your element of interest, and in the process, scatter an electron off of it. So for that, you must have a source of electrons, and you must overlap them with your atoms. So if you want to make that reaction work as much as possible, you want to confine it all. You want to make sure that they overlap as best as possible. So you need an interaction volume where both can be held sufficiently long for the interaction to take place. So how do we do that? We do that by having somewhat of a big volume in which this can happen. And that's the description of what we call the versatile arc discharge ion source, the VADIS, at Isolde. There is a cathode here that's heated up and that emits the electron. And here you have an anode with a voltage difference between the two of a few hundred volts that allows you to accelerate the electron from one to the other. The little holes you see in that blue anode are actually representing a grid that will let 50 to 70% of those electrons to enter your volume. You also have a magnetic field that surrounds your anode volume in there, so that's the cathode, and in red and in pink in that upper picture you have the anode volume, and around what is labeled magnet, it is an electromagnet that will provide a confining field for the electrons. You also introduce a buffer gas into that volume so that you can help keep those atoms in there a bit longer and sort of thermalize them from where they're coming. You may also use here a cooled transfer line. If you look at the design of this target, you have the target here, and then you go up through this orangey bit. It's actually orange because it's copper in that design. That's a very typical way of displaying copper. And the idea is you can run water, this blue dotted fluid in there, that allows you to cool this transfer line from the 2000 degree target to a few hundred degrees, maybe even less. And there you can condensate all the metals and make sure that the only thing that enters this volume are actually the gases. That is a very clever way through which you can actually get a pure beam by avoiding metals to enter your system. On those targets, you have a lot more parameters you can play with. You have the magnetic field, you have the anode voltage, you have a lot of geometrical parameters that you can play along with. And here is just an example of what one of my PhD students did, which was to scan the anode voltage. So she did it for a noble gas, krypton. Those sources are very often used for those. And you can see here how when you go above a certain threshold, you can start to see some ionization, but you need a voltage of about 75 volts before you actually really see a startup in the ionization process. So you need quite a lot of energy in those electrons, 70 volts, that's a lot with respect to what the typical ionization potential would be, which is for those of the order of 10 to 20 electron volts. And then she performed also that same investigation with gallium, where you can see here there is this onset and then the ignition, where you see really your gallium beam coming out. But then she also tried for fun to do a scan in rivers, and then she saw that there was actually sort of a hysteresis process, which took a very long time to understand. There are actually quite a few hypotheses as to what is causing this hysteresis, but it's not fully understood yet. And it does show that it is not simply what energy do you need for one electron to encounter one atom to create the ionization. You have a lot of things working in there. You have a buffer gas that plays in there. You have electric potentials that play in there. And all of those will have a very strong impact in the behavior of your ionization system as a whole, as a macroscopic device. And that's what we are currently trying to reconcile from the electron to atom interaction, trying to describe the macroscopic behavior of an ensemble. Another aspect that Giselle observed with her study was the load limitation. This is something that is very commonly known with iosources. It's not because you put more atoms in that you're going to get more ions out. And this is a crucial issue when you're trying to produce a high-intensity isol facility. You will choke on your ion source. There is only so much that mouth can give out. And if you try to pour more, well, this is not a goose. It's not going to give you more. So, if the ion load is too high, your efficiency drops. And we've seen how crucial the efficiency is. There are also other effects that might have competitive behavior. So here you can see what was happening in this case is that there was a mixture of noble gases, helium, neon, krypton, and xenon, all 4 of them coming into the system at the same time. And then she was monitoring the different content of the beam outside as a function of a mixture of CO2 coming into the system, creating a CO plus beam. And you can see that as you increase the CO current in the microamp scale, here you can see how you're dropping from this reference point. All of those are very much losing in their intensity. But the amount of atom of those different noble gases is not changing. It's just the efficiency that's dropping substantially, except for xenon. And then you look at it, and actually you've got the ionization energy of CO is 14 eV. And look where xenon lies. Of all of those, it is the only one that is below. So one of the hypotheses is actually you produce a lot of CO, and then you have a charge exchange process with the xenon. That means the more CO plus you have, the more likely you are to exchange those charges with the xenon and produce the xenon plus beam. But the same is true in reverse for the others. To have more CO plus beam, you need to have more CO in your system. And so it's more likely to give away an electron and ionize itself to neutralize those guys, which is why you see those efficiencies going down. Now, this is something that my new PhD student wants to investigate more systematically, because you see we have a lot of elements from which we can investigate whether you get enhancement or not. But that would mean that the CO could actually, it was described for a long time as being the poison of those Vadis sources, but it could actually be a controlled suppressor or enhancer, depending on what you want. And there you see there is a lot of understanding that's missing into really coming to a conclusion on those ion sources. And to deepen that understanding, you can also look at the potential. I won't dwell on this too much. It is a complicated picture to see, but the point is you have to look at the electrostatic potentials that allow you to extract something. You need to be connected here with this output, and you can see here how there is this blue area where everything is trapped and not coming out. But that depends also on your electron density and on your ion density. But those are simulations. Now we need to find ways to also experimentally challenge that. And that's what I wanted to tell you shortly on those 2 types of ion sources. Maybe it's a good time to have a break, and then you can come to me and ask questions if you want. Third ion source I wanted to talk to you about, the resonant ionization process. So, what does that entail? The one at Isolde is called the resonance ionization laser ion source. So you can see that's basically the laser ion source. The reason we call it resonant ionization is that you can have many forms of laser ion sources. You can have the laser-based Wakefield accelerator, where they go with femtopulse lasers that give you a lot of power, very compact in time. Not at all what we want to do. You can have the ablation lasers, where you just crank up the heat and basically blast material off and hope some of it will be ions. This is also not what we're doing. Here, you actually want to go hyper-selective into the properties of an atom in itself. And the way you do that is by finding resonant transitions in a given atomic structure so that you selectively excite an electron from the ground state up to one, maybe even several intermediary states until you resonantly bring it across the ionization threshold. And you do that by physically sending the laser light into your ionization cavity. That means through your dipole magnet. You'll see why that is important in a few minutes. And what you also need for that is a huge laser lab. Huge, relatively important laser lab, let's say. But if you look at how Bruce here is operating the lasers at Isolde, you can see that they have 1, 2, 3, 4 pump laser to go into 1, 2, 3, 4, 5, 6 tunable lasers, and they have frequency conversion units, even built into their cavity or externally, and then they have to send all of that with quite some complicated optics along a path of 15 to 25 meters. So it is not a trivial laser infrastructure. It is something that's very demanding, which is why your colleagues from the laser ion source for Isla Mira are not here today. Lucia was just telling me how they are actually today starting to tune up their first pairs of lasers so that they can actually start working and developing their own system here as well for the future. But it's never too early to start because it requires a lot of development and infrastructure to realize it. So let's look at some concepts. You want to select transitions in your atom which are going to be short enough that they will not be able to excite anything directly and non-resonantly from the ground state across the ionization threshold. You don't want to go into too deep UV. If you go into those very deep UVs, you might just blast electrons away because you give them enough energy. And if you look, I took for you what the lowest ionization energy was. That's that of cesium, and it comes to 3.89 eV, 940 terahertz, or 318 nanometers. So ideally, you want to target transitions that are above that because you want to avoid producing anything non-resonantly if you can. The second aspect, that's quite, and that's why you actually need so many transitions. Because of course, if you don't have enough to go all the way with one, well, you're going to need several to go all the way. The second thing you can see is that there are 3 different ways through which you can go across. You can have auto-ionizing states. Those are states that are across the ionization threshold. They're actually virtual states made by multiple electron configurations, so that one will actually be emitted at the price of the other falling back in. You can have also excitation to Rydberg states. There are atomic states that are very close to your ionization threshold, and if you apply electric fields, you can actually push down the ionization threshold so that they go below your Rydberg state, and then suddenly they become ionizing states. And the third way is just to give it enough energy at the end to go across the ionization threshold in a non-resonant way. But then comes the question of power. How much power do you need for those different forms of excitations? The resonant transitions here below, they typically saturate with very little power. Milliwatts are sometimes sufficient, maybe 10, 50 milliwatts, and you'll have plenty to completely saturate a transition. If you go to auto-ionizing states, you will need more because they tend to be a lot broader. So you're going to have to cover all that broadband. If you go with the non-resonant transition here, we typically never have enough power. You require watts of power to saturate that, and we just have to blast it. And we typically stay in the linear regime of that. If you try to give even more power, then you start to have heating effects. You start to heat the material along the transport, which gives you lensing effect, which completely screws up the entire alignment. So there is a limit in how powerful you can get in those. Note that too much power may also open new ionization channels, such as non-resonant 2-photon capture. And then suddenly a light at 532 becomes actually 2 photons adding up. You divide that by 2, and that's 266 nanometers equivalent, which you see will be able suddenly to blast a lot of things out. The other thing that's quite important is not so much your average power as your power density. At the time your photon flux will come in interaction with the atoms, you want to make sure you have as many photons as possible. And the way you do that is by compressing all that population in a typically pulsed laser system. Now, having nanosecond length pulses is sufficient. However, you require a high repetition rate to make sure that you will at least encounter an atom once in its passage through the ion source. So that's why those are operated at typically 10 kilohertz, which is rather demanding on those laser systems. There is also a nuclear component to resonant ionization. There are, if you look at the atomic structure, there are corrections onto this atomic structure that arise from the properties of the nucleus. First, you have the finite size of the nucleus. If you look at how you describe the hydrogen atom, you start from a point charge. If you actually go to describing a real atomic system, you have to take into account the finite size and the shape of your nucleus. And the result of that is a perturbation of 1 part in a million on the atomic energy level. You're going to say, oh, 1 part in a million, big deal. So, just for comparison, we said 300-ish nanometers, well, let's say 1,000 terahertz. Yeah, our lasers have line widths of a few gigahertz. A few gigahertz to 1,000 terahertz, you're in the 1 part in a million range. So 1 part in a million is not something you can actually neglect. It is something you have to consider carefully. And if you look at the size effect, here you have the full equation for it with the charge distribution coming in there, but also mass effects coming in here. And basically what it does is it perturbs all the levels differently, but in the end what you see is a change in your transition frequency. The second aspect is the hyperfine structure, which relates to the electromagnetic moments of your nucleus. Magnetic dipole, electric quadrupole, and so on and so forth. And those will lift the degeneracy on the magnetic substates of your atomic levels, creating a set of sub-levels which create such of a picket fence of transitions. So instead of having one nice transition, you start having, in this example, 6. And why do we care? Well, it's also 1 part in a million effect. So maybe your laser is broad enough to cover the whole, or maybe it's not, it can only cover one. And what if it does not cover everything in the same way? So first off, these two aspects will be key points that I will discuss in our next lecture on properties, but let's look at what impact it can have on production in the ion source. And here, you have to consider the balance between the resonance line widths you have and the typical isotope shift and hyperfine structure effects. So you are in a high temperature environment, 2,000 degrees. It creates a Doppler distribution. Basically, hot means flying in all sorts of directions. Flying in all sorts of directions means Doppler effect. Like, you know, the ambulance passing by and changing its sound, well, it's the same. Or the galaxies flying away from us. And here you have the same. And that distribution gives you a broadening of 3 to 5 gigahertz. We are also working with high power because we want to get as much as we can. That tends to shorten the lifetime of the states, which means an increase in their line width. And that typically contributes to about 1 gigahertz. So when you put that together, you have already quite a broad line width. So to match that, we work with lasers that typically have 10, maybe sometimes 20 gigahertz line widths to make sure that, you know, we get it. We're not going to miss it. And then you have, you can operate with reduced line widths down to 1.2. Say if you want to look at specific structure and investigate them. But then what are the scale of isotope shift and hyperfine structure? Those can actually vary a lot. From tens, hundreds of megahertz, then of course you don't care if you have 10 gigahertz line width. But if you look at something like the heavy elements, you can have 50 or 100 gigahertz wide hyperfine structure. And actually, 3 cases that are very specific are copper, silver, and gold. And then should be the question, why those? Now, if you try to think very carefully in your head, where do they sit on the periodic table? They're actually one on top of the other. And they all have the same property. They're a mid-periodic table, single S electron valence. And that single S electron has just a huge splitting in its ground state of several gigahertz. And that leads to the sort of pictures you can see, like in the orange and red here for 108 and 110 silver. You can see how that creates this big hyperfine structure because of the split in this ground state component. You can see that the red and the orange are not very much separated from one another. So there is not much isotope shift to worry about. But the hyperfine structure here is a big problem. And the other thing you can see is that 107 and 109, so in this time, completely different configuration. Basically, you only have, nuclear-wise, a single proton, whereas in the other one, in the even one, you have a proton and a neutron combining with each other. It gives rise to very different dipole moments, so that in those two, they vanish, and you get a single transition again. And in the red and orange, they actually amplify, and you get this very large splitting. It actually means that if you set your lasers right, you can get isotope separation from working with the lasers only. Better than that, if you see here, they're actually isomeric states. Technically, you could separate the isomer from the ground state with this technique, which is very exciting if you want to do detailed investigation of the different nuclear properties. So that's a very exciting aspect that you can have also with the laser ion source. And note that this simulation is done based on an enriched 107 silver sample that was irradiated in the ILL reactor, just to see what would be there. So the different intensities represent how much of the different silver isotopes there are, and by using the lasers at the right frequency, you can completely suppress the leftover raw material and really enhance the 108 that you want. But what you see as well is one laser will not be enough. You need a laser here and a laser there, so you need two lasers to make it work. Developing those ionization scheme is also not trivial, and it takes a lot of trial and error. For each element, you need to restart the work from scratch and have dedicated investigation to identify the best scheme you can have. And you have here some of the different searches that I've been involved with in polonium, astatine, and radium. And you can see some are a bit crazy, like in the radium, we actually have to wait until this second excited state after the 784 nanometer transition decays into another one to get to our most efficient scheme, which is something that had never been observed before. Not that it does that, but that this would be actually the most efficient scheme was quite surprising. Note as well that in some cases, you may have a split in the ground state population. It could be that you have two states that are so close in energy that they may be thermally populated. And then it will reduce your efficiency, or you will have to use multiple lasers to make it work. The literature is a good starting point, but sometimes there is no literature. If you look up the ionization or the atomic levels of plutonium, you will find nothing. When we looked up what is known about astatine, those two blue lines at the bottom were postulated as potentially maybes. And that was it. Nothing else was known. In the polonium, there was a study from the 60s that said, we've seen some of this. Good luck. And nonetheless, we were able to create those very extensive ionization scheme for those different elements, which are now very standardly produced at Isolde. But there again, we come to the same limit that was described before, the load limitation. It's not because you have a good ionization scheme that you'll always produce a lot of what you want. You actually end up having a limit with how much can come out. And in this case, it was not the CO+ beam that was used, it was a rubidium beam that was created. And you can see as your rubidium beam suddenly shoots up, your laser ionized gallium beam goes down, and that one is surface ionized. Rubidium is an alkali. So there is a problem there. The more beam you have, the less beam of what you want you may get. So you need to find alternatives to overcome this problem. So that's a big source of research. Do you have questions on ion sources as a whole? don't see any. Well, you can come to me afterwards as well to discuss different things. But let me go quickly through some of the beam manipulations. Basically, looking at the time structure of your ion beam can be quite interesting. But then you first have to start with the time structure of your primary beam. If you look at Triumph, they have a pseudo-continuous driver. It's a cyclotron, so technically it's a pulsed machine, but the repetition rate is very high, and the time definition of the bunches is very poor, so that after they fly the however many meters they have to, they sort of catch one another, and it ends up being more like a slightly modulated continuous beam impact. But at Isolde, we work with the proton synchrotron booster, which has a period of 1.2. It's a synchrotron. It's got very well-defined bunches. Actually, there are 4 bunches of a few tens of nanoseconds separated by 100 nanoseconds each. So it's really like a tack train that comes onto the target, with a multiple of 1.2 waiting times, because it's actually not all the pulses that come to Isolde. Note that this means a very high instantaneous power deposition, even if the average power is quite limited. Now, Isola Mira will be somewhere in between. It will be multiple times per second that you get the beam on target, but it should still be a well-defined bunch that comes every time. So then one will have to see what it means in terms of time structure. But then, when you look at the radioactive ion beam, you have diffusion and effusion processes that take their own time to get out. So basically what you see is a convolution of those release times and the irradiation time you have before. And that will depend on your target material, temperature, on the element itself, and on the half-life. Because if you have something short-lived, it may actually decay on the way. And that gives yields to such a profile for the release, where you have here a proton coming on the target, and you will start, or a bunch of protons, and then you will start to see your material growing up, but suddenly the amount of material will start to drop, and then you have this long tail for what we call the slow component. And to that, you convolute the half-life. And in practice, it gives rise to that sort of behavior. Here, it's a study that one of my students did on the behavior of gold, and each of the vertical bars here that you see is actually a proton pulse. And you can see how they all add up to give you this sort of behavior on, here it's not the number of material we see, it's convoluted with the decay, it's the number of alpha particles we measure, but it's quite similar. And the reason we did that is because our measurements stopped here, but you can see with the red line, we're not measuring everything. And we wanted to compare with another element that is in the decay chain, the platinum, and you can see how when you, based on that, estimate how much platinum would be, that we miss a lot of what could be measured of the platinum because of its longer half-life. So it was to get that correction factor. But the point is that the red line is not fitted to the data. The only fit parameter is that the integral of the red up to here is equal to the integral of the data. That's the only fit that has been done to this. The rest is purely based on our understanding of the release of gold. And I think it's quite a fascinating picture to see that it works so well. So I will skip the radio frequency Cooler buncher because time has already run out, but they might be interesting for next lecture. And I wanted to quickly come back to the mass separators, because it's an important part of the manipulation, and sometimes people don't realize, oh, you put a dipole magnet and you're done. No, it's not just that. So actually, we can play the 10 differences. Do you see the difference between this guy and that guy? Between the lethal magnet and the Medicis magnet. What differences do you see? Yes, indeed. I was hoping someone would say one is gray, the other is red. That would be the starting point. It's actually the same magnet in both cases, right? It's the magnet from the lethal facility, the Leuven ISOL in Louvain-la-Neuve, that we shipped to Sun Medicis a few years back. It was painted red to match the color standard of the dipole magnet at CERN. But the point indeed is that this little port here that you do not see there, and that's why I could not shine the lasers in the right direction in my PhD, because we didn't have that, but because of the big concrete wall around it, we could not open it up to put it. So when we shipped it to CERN, the first thing they did is open it up and put a window. And actually, it's not only putting a window, it's what is the effect of the window on the homogeneity of the magnetic field. And that has a really big impact. So you cannot just neglect it. You have to really consider it thoroughly. Luckily for us, if you see here, the changes were a bit on the edge, but they were not substantial. And in the end, we could still use the magnet in spite of that new window. That was good. However, the other thing you see as well is how there is here this little piece around it. It actually disappeared there. It's one piece of, it's a correcting coil that was put at the end that got lost somewhere and discarded as junk, which meant we could not recover the mass separation power here because the entrance of the magnet here was actually not sufficiently homogeneous anymore. So we needed to rebuild it, and it took us another 2 years before we could actually start working on the actinium isotopes, because we could not separate such a heavy beam at a time. So that's why it's quite important to look at these things. Something that's also cool to notice, your focal plane is not perpendicular to the beam. It's actually, depending on the mass, it's going to come at different distances along the beam. I thought it was quite a cool feature when I realized that. And that's what you get at the end from the separator. So here it's the representation of the Medicis separator bunker, and here you see how laser ionized terbium was separated from natural gadolinium in which it was embedded. And here you have a mass scan that was recently performed from a tantalum target that had been irradiated at Isolde, and you can see the sort of different beams that could be produced from it. So that was with surface ionization only. And you can see, as I mentioned before, how chromium is a remnant of your target material. You get a few things like the alkali that are very well ionized, an alkali earth here, and that's also an alkali earth, and the aluminium, which is one of those weird elements that tend to go below the threshold that's needed for surface ionization. How do you feel about me going another 10 minutes? Your call. I see a few people had to leave, so they've departed already, but otherwise I will continue. And I promise next time I'll do my best to be more concise in my rendering of it. So I want to come back to the efficiency in the release, because that's really the key. How do you get as much beam at the end? You get your best cross-section, you get your best luminosity, and you get your best efficiency. And this is where there is a lot to be gained. So, limiting factors are diffusion effusion, whether it's partial or total limitation. As we said, a refractory don't come out, but also delays that lead to decay losses. Then you have to consider your ionization efficiency, which depends on your element and on your ion source load. So you're going to have to find a solution for that. And then you have the separation and transport that are well under control. And remember this time structure which plays against the half-life. So how do you first tackle the ionization efficiency? Well, you try to define your ion source, but you need also to measure it. And so what we've done, or what we quite frequently do, is actually measure those efficiencies. And here you have the study of the ionization efficiency of mercury in the Vadis ion source, where they put a known sample, a known volume of mercury in the source, and then they just let it run. And they integrate this current reading just to see how much they've actually managed to get out. And they ended up with 10%. The reason why it looks so spiky is because as it started to seem like it was going down, they would just crank a bit the heat on the oven to make more mercury come out, but they didn't want to put too much mercury at once, because otherwise they would have reached load trouble. So they were trying to keep it, you see, under the 80 to 100 nanoamp mark to make sure that they get the best efficiency, not damage that efficiency with too much beam. It was part of a test. You could say, you could argue, no, I want more, but then you would have to find solution on how to recover your efficiency. And you can see here how that measurement was not too bad. It took about an hour and a half. Now, we did the same to measure the efficiency of actinium-225. In that case, it was a sample of actinium from the Joint Research Center in Karlsruhe that was placed in this little thing that we put in our target. And you see here the same picture as you had over here, which is our signal, where you can see also this baseline here that ends up being negative. It's because actinium is actually radioactive. So as the radioactivity is emitted from the Faraday cup, you start reading a negative current. So we had to systematically correct for the beamline to get the right value. And here underneath, you have the activity of actinium actually calculated from that current in red and compared to activity from a decay product, bismuth-213. Sorry. As measured by a cadmium zinc telluride detector we have in our chamber. At the end of this study, we also concluded we had about 10% efficiency, actually correcting for this little bit in green here after a few hours where we were stopped, and for the uncounted time before zero, we estimate that we could get to 13%. Those are huge numbers. Typical ionization efficiency are 1, maybe 2%. And here we're talking for mercury in the VADIS and for actinium in the REALIS to about 10 to 15%. Those are really impressive numbers. Note, however, how long it took us to do that in this case, and that was about a day. Then you want to look at effusion, which is how does it come out of the material, how does it come through the volume. For that, we actually repeated the actinium measurement, but this time embedding it in a thorium oxide material. It was not from the grain, so you don't have the diffusion, but it was cooked at some 100 degrees or so that it seeps into the material itself. And there, we recovered actually the efficiency. However, you can see how our activity, as measured by the bismuth-213, was very little, nothing, and suddenly shot up as we increased the heat. So then we realized we needed to operate at 500 degrees more than in the pure ionization test. And for that, I called in your colleague Benji to do some calculation for us on what was happening within the thorium oxide. I asked Sophie here to do some thermal calculations so that we get a better understanding of this. And in the end, it seems to be that we had to break down actinium oxide, which was forming onto the thorium oxide. Then there are diffusion studies you can perform. So here, that's a setup that was designed by Simon, one of my PhD students, where he put the target material in here, and this is the same structure as the Isolde target so that it could be brought at the ionization point. And then he opened that, he had put some pellets like this inside. He then used a setup in which he first measured the activity he had in his sample from whatever had been produced. You can also work with FLUCA simulation if you don't have this opportunity. Then he inserted this long tube into an oven from which he could very easily control the temperature. Had a gas leak from here, a leak tube that was placed inside so that he could expose his material. In this case, he wanted to release carbon-11, so he wanted a CO beam. That means adding oxygen into the setup. And at the end of this, after his treatment of a few minutes, he took it back out and with exactly the same setup, measured the activity again. And by comparing the activity before and after, correcting for radioactive decay, he could actually estimate how much was released, and in his case, it was about 10%. From that study, he was actually able to determine the diffusion coefficient in his boron nitride target, and that actually matched very well with that of carbon in, the parallel of boron in carbon. So carbon in boron nitride behave like boron does in carbon. which was quite an interesting observation. So with that, you technically should be able to have the full analysis. And now, what happens is you actually look at those different releases. But now I'm not plotting here the yield, but I'm plotting the total efficiency by comparing what we see at our experiment with respect to what FluCap predicts is happening inside the target material. And you see, if you plot that as a function of the half-life of your element in polonium or actinium, that you, both cases, have sort of the same behavior. And that actually matches very well with the different parameters we care for, which is the ionization efficiency, and typically you asymptotically come to the ionization efficiency, which in the case of polonium was not quite 1%. But you also have two kinks in that curve, which correspond to the fast and the slow component from the typical release profile you see at the top. And you see then how improving those release will mean not only improving generally the production, but especially the production of the shortest lived isotopes, because you will basically keep the kink at much lower value so that everything is lifted up in intensity, in efficiency, and thus in intensity. Voila. So that brings me to post-acceleration. I think that it is not as crucial for this lecture, so I will not go in detail into it, and I will move directly into my conclusions for today, because we are already 15 minutes over time. Sorry, it was me trying a very cool animation on the drift tube LINAC. So what I wanted to bring to your attention today is that we have different sort of targets for ISIL facilities and how we need to tailor them and develop them to match the needs of what we want to produce. There are many, actually so many, it would be impossible for me to give you all the overview of what's happening. There are also new material that are under development. Two of your colleagues are missing today because they're currently at Triumph in Canada testing the latest target material they have developed. And I did not include it in this presentation because I'm too anxious to see their results before we can make a full story about it. We've also discussed ion sources, how we also have to adapt those to each element of interest, and that each require extensive investigation, sometimes ongoing, and maybe closer than you even think. Somebody in the room here is doing such development, for example, on the surface ion source. The beam distribution is then determined by different parameters impacted on by the primary beam, the target material, the ion source, the element of interest, the isotope half-life, you name it. There are a lot of things that come into it. And basically, every time you want to design an experiment, you're going to have to think about, okay, how do I tailor all the parameters to the needs of the science I want to do afterwards? You can also manipulate this beam to deliver the best solution to each experiment in terms of time structure, but that I skipped on the RFQ cooler bunchers because of time. Beam emittance as well from the RFQ cooler buncher, and also in terms of beam energy, that's the post-acceleration that unfortunately we didn't have the time to cover. There are also many other things that I have skipped. I didn't talk to you about molecular beam, for example, how you can create molecules to make things more volatile. This is some research that's ongoing at the moment, and we have PhD students investigating that at Isolde. Or how you can also manipulate atomic states in the cooler buncher. This is a technique that was developed at the IGISOL in Uvascular, and that has allowed them to open up a lot more different studies than what they have done before. So there are a lot of things that you can do with those beams. And in the short time I had today, I tried to give you some of the keys of what was going on, but of course there's a lot more. Thank you for your attention, and I'll see you next week.